A warm welcome to everyone and thank you for joining the webinar. My name's Dave Marshall-George and I'm the Sales Director for Condair here in the UK. And with me today is Paul Kipp. Paul's the Area Sales Manager for Condair covering the north of the UK. We're going to have over 500 people on the webinar today from lots of different countries, so everybody will be on mute. But if you have any questions, please feel free to submit using the text question function in the control panel. Paul will answer some questions as we go, but when the presentation is finished in about 45 to 50 minutes, I'll be addressing some of the most popular questions for you. I'd like to draw your attention to the documents available for download from the materials icon on the control panel. There's the presentation in PDF format, there's a 10-point guide to humidity control in clean rooms, and there's a digital copy of the psychometric chart. And as a reminder, about an hour or so after the presentation finishes, you'll get a link where you can download your CPD certificate. So with no further ado, I will turn my camera off, as will Paul, so you can concentrate on the slides, and we'll continue with the presentation. So as a brief introduction to Condair, Condair is a privately owned company with over 1,000 staff. Our head office is in Switzerland, and we've been a world-leading producer of humidity control equipment and evaporative cooling equipment for over 75 years. And we manufacture in Hamburg, in Ottawa, Beijing, Denmark, and we export globally. So our learning objectives for today are: firstly, we're going to look at what our clean room's humidity needs, and then we're going to look at humidity's relationship with temperature and how accurately to raise humidity and how to accurately lower humidity. And then we're going to look at some energy considerations at the end of the presentation. So what are a clean room's humidity needs? Well, we can split this into 4 categories. Firstly, the moisture equilibrium, and we're not so much talking about the moisture in the air here, we're talking about the equilibrium in the product. Now that could be a pharmaceutical, or it could be anything where we're producing that has a moisture content that we want to maintain. To maintain the water content in that product, we have to have the appropriate relative humidity to maintain the moisture content within the product. If the relative humidity is too low, then moisture will more readily leave the product and can have an adverse effect on the product. Whereas if the relative humidity is too high, we could have moisture entering the product. So maintaining the equilibrium relative humidity in the product is critical for maintaining product quality. Next is preventing static buildup. Well, static is caused by an imbalance of electrons between 2 objects, often occurring when we get contact and separation and contact and separation. Then, depending on the materials involved, electrons can leave one object and collect on another. So if we get 2 objects that have an imbalance of electrons, you'll get either attraction or repulsion. So if we've got a conveyor with product on it, and if we've got a negatively charged product coming into contact with a negatively charged item, then we can get a repulsion. And if we get a positive and a positive charge, then we'll also get repulsion. Then if we have a positive and negative charges, we get attraction. So that can cause issues when you're running production through a clean environment. So we prevent that by increasing the relative humidity in the clean room to a point where the imbalance of electrons can be distributed through the moisture molecules in the air, and then the air then dissipates that static charge. We also want to make sure that there's no possibility of a static charge dissipating through a spark. That could be a potential ignition point. We may also want to prevent a reaction that could happen with either low humidity or high humidity that could be within a product. We also require a clean room very often to remain within a tolerance for testing purposes, and that will typically be defined by the scope of the test. So that's some of the reasons why we would control humidity in a clean room. So there are lots of industries using clean rooms. It could be a university lab where we've got research facilities. It could be a pharmaceutical production for testing. It could be a myriad of reasons why they're using those clean rooms. Say it could be pharmaceutical production. Again, we're maintaining the moisture content of pharmaceuticals and ensuring that static isn't interfering with the production. Let's say we've got a series of blister packs that are going along a conveyor and they're being filled by dropping tablets into them. If we have a negative charge conveyor contacting a negatively charged packet, then we could get repulsion, and that can cause problems when you're dropping tablets into the packaging. And again, we want to maintain the equilibrium relativity of the relative humidity of the product to ensure that it forms correctly and that the coatings are correct. And of course, to make sure there's no reaction between the pharmaceutical and the packaging. And also, the equilibrium relative humidity can have an effect, an adverse effect, on the efficacy of the pharmaceutical, so how well it interacts with the human body. So it's absolutely critical that we get that right. And biology is also an issue. We may want to make sure that any bacteria is controlled by maintaining optimum relative humidity within a space. And also, if we're producing samples or growing cultures in a lab, then the environment can be critical to how those cultures will act and how they'll develop. So again, we specify relative humidity. Typically, that will actually be specified by the biologist. Cosmetics and perfumes, again, this comes down to product quality, and we need to ensure that products that are produced have the right shelf life, that they have the right colour, appearance and structure. And ensuring the equilibrium relative humidity in the product is critical to making sure that that happens. PCB and electrics, again, the issue here is typically static that we're trying to reduce, and the static discharge can be quite significant. A very small static charge can be generated and actually unnoticed by us as we can't perceive some of the small charges that could damage a PCB or electronics. And again, we humidify to over 45% RH to enable any imbalance of electrons to distribute through the air to prevent static buildup. It's a more holistic approach than just local static prevention. It's a very similar story with semiconductors. We don't want static discharge interfering with or damaging a semiconductor. So it's critical to be over the static threshold. Lithium battery production is a good example of where we want low relative humidity because we have the potential for a reaction with moisture and lithium. And this can be explosive. So generally, moisture content in these applications has to be ultra low at around 3%. Food production, when maintaining the quality of food and the appearance and shelf life of food, we maintain that equilibrium relative humidity within the product to making sure that it doesn't take on moisture and it doesn't emit moisture. So we're maintaining the quality. And a bit more niche one is a medical cannabis. Is a good example of where we may want a varied condition in the clean room because the plant will require different conditions at different stages of its plant development. When it's developing its roots, it will require a certain level of relative humidity and temperature. During its primary stem development and leaf development, there's an optimum temperature and relative humidity for that. So there are many reasons why we control humidity within a clean room environment. So what are the humidity control needs for a clean room? Well, here's a good couple of examples. On the right-hand side is a humidifier, in this case a resistance heater humidifier that we'll talk about in some detail shortly. On the left is a desiccant dehumidifier. Very common to see this type of unit in a clean room. But one of the issues that we have in a clean room environment is to control particulate matter. So we don't want any machinery that could put any particulate into the airstream and hence into the clean room. Now with a steam humidifier, when you're producing atmospheric pressure steam, we know we're in a good clean steam environment. because all the minerals in the water get left behind in the humidifier. And we're just putting steam and atmospheric pressure into the space. So very, very minimal potential for risk of particulates. With a dehumidifier, typically we're taking the air from the space, from the clean environment, putting it through a dehumidifier, drying it, and then putting it back into the space. Now, as we're only taking it from a clean environment, and the only risk is any particulate that could come from the silica rotor, typically we've also got a filter on the outlet side of the dehumidifier, so it's very, very small risk. We have to make sure that the balance between the regeneration air and the supplied air is controlled within the dehumidifier to ensure that there's no bypass happening with external air going into the recirculating air. But this is part of the commissioning process of the dehumidifier to ensure that doesn't happen. We also need to ensure that we have consistency of control to make sure that the clean room is operating consistently and to ensure that we don't have any downtime due to our lack of control or other situations. We also need to consider the accuracy of control that the client requires in the clean room. So the type of equipment that's employed will have a bearing on what's achievable, and we may need to consider the flexibility that experiments that start at one condition and then in 2 years' time, when the study's finished or the production is finished, we may need a different environment. So building in a bit of flexibility in the design and the controllability of the equipment is essential to meet that degree of flexibility and kind of future-proof the clean room. So we need to look at humidifiers, dehumidifiers, control particulate matter, have consistency with uptime, and have accuracy of humidity control and that degree of flexibility over time. So next, we're going to look at humidity's relationship with temperature and why it's critical to understand that relationship. So on this slide, you can see we've got a blue dot, and that blue dot represents 5 grams of water vapor in air at 2 degrees C. So at 2 degrees C, 1 cubic meter of air with 5 grams of water in the air is completely saturated. It can't hold any more water. But let's say we increase that air temperature to 10 degrees C. Well, the air now has expanded. It can hold twice as much water, but the absolute moisture content has stayed the same. We haven't put any moisture into the air or taken any moisture out of the air, but the percentage saturation has fallen to 50%. Well, let's say I increase that temperature even more. And let's now say we have air at 20 degrees C. Now for 20 degrees C, I've still got the same amount of moisture, but I can hold 75% more water, so I'm only 25% saturated. So the amount of moisture in the air is the absolute moisture, but the percentage saturation is the relative humidity. The percentage saturated relative to the potential amount of water that can be held. So we can see that the relative humidity is going to change with the temperature. So these are things to consider when we're looking at the profile of a clean room. So in the clean room, we could have hotspots in an area. We could have hotspots around machinery, could be hotspots around a person, could be around a PC. It could be around any source of sensible heat that's going to have an effect on the relative humidity of the air around that item or person. And we could also have cold spots. Could be an outside wall, could be a glass window or an air conditioning vent. These could all result in high humidity. So we have to be aware of these things when we're looking at the profile of the room to ensure that we've got sufficient air going through that clean room so it's going to handle these issues. or we need to just design around it to ensure that we're giving the correct relative humidity at the critical point of the process. So temperature not only impacts the humidity across a room's air profile, but can also create microclimates next to a material surface. So it's important to be aware of this when dealing with hygroscopic items that are either colder or warmer than the ambient air. Products cooler than the air will chill the air directly next to the material surface, creating a zone of high humidity. If this reaches dew point, then condensation can form on the surface. If the material is susceptible to moisture, such as a powder, then an increased humidity, even without condensation, could potentially result in absorption and moisture movement from the atmosphere to the material. Likewise, if the product is warmer than the air and is hygroscopic, exposure to the air will cause drying across the surface through evaporation. So we need to consider potentially acclimatizing materials to a production environment prior to enwrapping or exposing them to the air, or alternatively, adjust the ambient humidity to prevent issues from moisture movement. So now we look at how to accurately increase humidity. Now, as mentioned before, to accommodate a range of processes in a clean room without needing to retrofit the HVAC system each time, being able to offer accurate and responsive humidity control will fulfill a wider range of clean room projects. Now, there are typically three types of control from a humidifier. The first would be on-off control. An on-off control with a humidifier, we have to consider the inertia to get the water boiling and allowing it to cool and react to a control signal. So when we get a demand signal, we're going to be heating the water, and typically we'll reach set point and it'll turn off, but the water will continue boiling for a while, so it will overshoot. The humidity will then fall, and then the controls will call for the unit to be turned on again, and we've then got to start heating the water again before we start to meet the demand. So we get quite a wide tolerance with the humidifier with on-off control. If we go a step further and go to stage control, and then we're stepping potentially one electrode or one series of elements on and off, then we get slightly better control, plus or minus 7% typically with stage control. But typically with a clean room, we want better than that. We want modulating control. And when we put modulating control in, we can send a control signal to the humidifier, and we can pulse current to the heating elements at a rate relative to a control signal. And that will give me a fully modulating unit that will modulate between 0 and 100% of its output, and will rapidly react to a changing environment. So considering the type of humidifier and the controllability of the humidifier will be critical. Next, we're going to look at 4 types of humidifier that we offer to give this fully modulating performance. Well, firstly, the best option typically is a resistive heater humidifier. And here we use a series of heating elements inside a stainless steel boiling chamber, and we modulate the electricity going to those heating elements via a series of solid state relays. And they're going to switch electricity to those heating elements at a rate relative to the control signal. So we can modulate that control signal from 0 to 100% of the unit's output. By doing this, we get very tight output control. Running on mains water, typically we'll get plus or minus 5% RH control. When running on RO water, and we then don't have to run in dilution cycles, we can get plus or minus 1% RH control. And units have a range of outputs from 5 up to 160 kilograms an hour for each. And each system will be comprised of a number of boiling modules, and each boiling module will produce 40 kilograms of steam. So again, we get fast response from those systems, and of course they're easy to install and retrofit. And a system such as this has built-in scale management. So as steam is produced, scale forms on the heating elements, but as the heating element expands and contracts, scale is repelled off those heating elements and then falls down to a scale collector at the bottom of the unit, which can periodically be emptied and maintained by the facility engineer. So easy to manage and giving good, reliable control. Now here, though, we are using electricity to produce steam at atmospheric pressure. If we don't want to use electricity to produce steam, but we still want to have a high degree of accuracy, then we would go with an adiabatic hybrid system. So this is an adiabatic hybrid system, and it utilizes dual technology, where reverse osmosis treated water goes through the RO plant, an ionization plant, and then we have a nozzle array spread across the cross-section of the air handling unit. When we get a demand signal, one or a number of these nozzles will turn on or off, and we will spray water into the air, which will be evaporated. And then any water that isn't evaporated is captured on a ceramic matrix, which then evaporates the moisture off in the same way that an evaporative humidifier would. So it's using two types of technology. Now in this instance, we're not using electricity to produce steam, but we still want the water to change its state from a liquid into a gas. And to do that, the water is going to suck heat energy out of the air, as it changes its state from a liquid into a gas. So the net result is that we need to preheat the air to give the air that energy required for that change of state from a liquid into a gas. So we need to look at the option of, have we got a cheaper energy source than electricity? And if we have, then this type of system really comes into their own. If you've got some form of sacrificial heat, or you've got runaround coils, you've got ground source heat pumps, some way of getting that preheating energy in a cheaper way than just using electricity, then you can dramatically reduce your running costs of your humidifier. Now, there are other types, and here's two other types of system. Well, firstly, there's an ultrasonic system. Now, this system uses a series of oscillating discs that oscillate at a very high frequency, and that agitates the surface tension of the water to produce a mist. Now, they're low capacity, really below 20 kilograms an hour. And again, it's an adiabatic system, so you need to consider preheat, because we're going to be sucking heat out of the air to change the state of the liquid. But you've got to use water treatment. If you don't, then minerals from the water will go from the humidifier up into the clean room. If you're putting it into an air handling unit, again, we have to be aware of water treatment and absorption distance and unit size. Now, we may have an existing steam supply, especially if it's in a pharmaceutical application. And we can utilise that and tap into the steam supply and put the steam through a valve and then through a distribution manifold, as you can see in the humidifier on the right. When the valve opens up on the receipt of a control signal, then steam is metered into those lances and then distributed into the ductwork or the air handling unit. And typically, you get a control tolerance of 2 to 5% RH. The capacities for these units are much higher. They go from 5 up to 1,000 litres an hour. And stainless steel versions are available if you require clean steam. Now, both hybrid and ultrasonic units must be operated on water that has low mineral content. Resistive steam can be operated on mains water, but this results in dilution cycles and more service requirements to manage the scale that's left behind. A reverse osmosis water treatment is frequently used in cleanroom humidification. It results in closer humidity control, because we have no dilution cycles to manage mineral concentrations, and reduced service requirements. And you can feed multiple humidifiers from one RO plant and be controlled by one humidifier. And we saw earlier that accurate humidity control is impacted by variations in temperature and also impacted by the performance of control strategy that the humidifier is using, whether it's modulating, stage, etc. In addition, it's also greatly impacted by the sensor. Well, the sensor sending a control signal to the humidifier will also have a variance in its accuracy. And typically the humidifier's accuracy will be at best twice the accuracy of the sensor. So a plus or minus 2% RH accuracy on the sensor will result in a plus or minus 4% control accuracy on the humidifier. And location is critical with sensors. We could have averaging sensors across a room. We could have sensors in the return air. It's not generally advisable to put a sensor in the supply air because the sensor can more easily saturate and be affected by the air on temperature, which could typically be different to the room temperature. So if you do want to supply a sensor to the supply air, then it's best to sense absolute humidity. And there we can see the variance. If we have a set point of 40% RH, we have a variance for the sensor, and then we have a variance for the humidifier. One of the big considerations with putting steam into a duct or an air handling unit, especially when you're dealing with a clean room, is this steam absorption distance. So this is the distance required for steam to leave the steam pipe and be fully mixed with the air. And now in a standard HVAC application, you would expect that to be something around 900 to 1200 mil, depending on the air velocity, the air volume, and the air on temperature and moisture lift. But with a clean room, typically the last thing in the air handling unit is a HEPA filter. And when we have a HEPA filter, we need 2.5 times absorption distance. So that's critical that that's allowed for either in the duct or in the air handling unit. We also need 250 mil before the steam lance to ensure that the air is laminar going onto the steam lance. And if you are sensing in the supply air, then the sensor location or high limit stat must be 5 times absorption distance from the steam lance. So again, these are all part of the system that are going to have a critical effect on the performance and ensure that the system isn't going to wet out. So next, we're going to understand how much moisture we're going to need to add to the air. And this is vital in technology selection. And to do this, we use a psychometric chart. Now, the basic elements of the psychometric chart are we have dry bulb temperature starting at the bottom of the chart at -10 and going up to 60 degrees C. Then we have the wet bulb temperature going diagonally down the chart. There's 15 degrees C wet bulb, 16 degrees C wet bulb, there's 20 degrees C wet bulb, and so on. We also have moisture content in kilograms per kilogram of dry air, also expressed as absolute moisture content in some terminology. We have the specific volume shown in meters cubed per kilogram. There's 0.85, 0.86, 0.87, and so on. And we also have the specific enthalpy shown in kilojoules per kilogram. And we plot the specific enthalpy by taking a condition on our chart. Let's say we're 20 degrees C dry bulb, 14 degrees C wet bulb. We would be at 50% relative humidity. So there's 50%, 60%, 70, and so on. So at 20 degrees C dry bulb, 14 degrees C wet bulb, 50% relative humidity, we'd be at 0.84 meters cubed per kilogram. And then we can plot a line from the specific enthalpy here, intersecting our condition, and then going down to the bottom scale, and where the value of the bottom scale and the top scale is the same, will tell us the specific enthalpy and dictate the line of process for an adiabatic humidification or desiccant dehumidification. So they're the basic elements that we're looking at. And if we're looking at an isothermal humidification process and looking to design it, the first thing we need to know is geographically, where is the site? So we look at local weather data and work out what is the worst case winter design condition. But we don't always know where the site is. So a pretty good rule of thumb in the UK is to use -6 saturate. So if we're -6 saturate, we're right here, -6 at 100% saturated. So if we take that air from -6 saturated and we heat that air up sensibly up to 21 degrees C, we've increased the temperature, or dry bulb temperature, but we've decreased the relative humidity from 100 to 15%. So then we isothermally humidify to increase the moisture content and relative humidity. And the psychrometric chart is telling us the moisture addition required for that process to happen. So here we've drawn the psychrometric process for increasing the dry bulb temperature and increasing the relative humidity. And it looks quite straightforward, but it does tell us some critical information. It tells us that if we want to move these things around, and let's say we're designing a system to supply air at 14 degrees C to give us some optimum cooling, well, we would then be heating up to 14 degrees C and then isothermally humidifying. But by the time we get to the absolute moisture content that we require, we'd be up at something like 80% RH. And 80% RH is the maximum you should see in an air handling unit or a duct. That is because it's only a very small change in temperature that will be required that would cause wetting out through any cold bridging or cold surfaces. So it's critical that we know what the condition is going to be, because this will also affect the steam absorption distance. The colder the areas that we're putting the steam into, the longer that steam absorption distance is going to be. So we need to look at these things holistically. So that's our isothermal process. But let's say we wanted to use an adiabatic system, like the system that we saw earlier. Well, with an adiabatic system, we know we're not putting electricity into the water to make it boil. We're asking the water to get all of the energy required to change its state from the heat energy in the air. So we've got to preheat the air. The good thing is the psychrometric chart is going to tell us how much. So if we go from our -6 saturate and we draw our line across, and then we plot the line of enthalpy, this tells us the preheating required to offset that decrease in temperature. So when we've done that, we can then adiabatically humidify up to our set points. And again, it's going to tell us the moisture content and moisture addition required for that to happen. But I have to accommodate that additional heat. Now, you'll notice that the start point, as far as the specific enthalpy, and the end point is the same. So it's the same amount of energy involved in both processes. The difference is where you get the energy from. With an electric system, it's using electricity. With an adiabatic system, you're using preheat. And again, if you can find a way of getting that preheat more efficiently, through ground source heating or scavenging heats, or however you can get that heat, waste heat, then it makes an adiabatic system a lot more attractive because of the energy run costs. So to determine how big the humidifier is going to be, we need some design criteria. We need to know how much, firstly, how much air we're trying to humidify. We want to know the external ambient at the site conditions, and we want to know the internal design condition. And from that, we can plot the moisture difference between those two conditions in absolute terms. And then we would look at the specific volume at the critical point of the process. So then that gives us a calculation where we take the outside air volume, we multiply that by the moisture difference, we multiply that by 3,600 because we're going from meters cubed per second to kilograms per hour, and then we divide that by the specific volume. So here we've got 1 meter cubed per second multiplied by the moisture difference, 0.0056, multiplied by 3,600 divided by the specific volume. Gives us a pretty good rule of thumb actually, because the answer to that is 24 kilos an hour. I use 25 kilos an hour as a rule of thumb for every 1 meter cubed of fresh air because it's easier to multiply up. So it's a really useful rule of thumb. So that's how we can accurately increase humidity. Now, how can we decrease humidity? Well, here there are two different kinds of technology that can be employed. Either a condensing dehumidifier or a desiccant dehumidifier. And again, they are completely different, and there are different considerations to be made and different reasons why you'd use one or the other. So we're going to dive into how these units work so we understand that. So a condensing dehumidifier is basically a direct expansion refrigeration system. Here you've got a pretty recognizable diagram of DX system. Here you've got a compressor that's going to change the pressure of a gas so it condenses at a given temperature. That goes through the condenser, but at the end of the condenser, then we have a pressure changing device where, as we've condensed the refrigerant back into a liquid, as the liquid goes through the pressure reducing valve, or typically a thermal expansion valve, we then change the pressure so the refrigerant will boil at a much lower temperature. And that refrigerant then goes into our evaporator coil. So this is your evaporator coil. So as refrigerant is traveling through this coil, by the time it's got to the end of this coil run, all of that refrigerant has turned back into a gas. It is evaporated. That's why we call it the evaporator. And that gas then goes back to the compressor and the whole cycle starts again. And the resulting effect of that is that we have a cold coil that we're blowing air over. So as we blow air over that cold coil, the air drops below its dew point and condensation occurs. And here you can see it dripping down into a water collector at the bottom of the unit. So as air travels over that cold coil, the water condenses on the cold coil and dehumidifies the air. So then you've got cool, dry air. That air then goes over the condensing coil, where it picks up the heat from the condensing coil and then goes into the space. So that's all contained in one unit. Inside the unit there, we've got an evaporator coil, compressor and condenser, and the controls and the fan. Now you may think that as the DX refrigeration system is a closed loop, that we might expect that the air on temperature and the air off temperature is the same. All we've lost is some moisture, but it isn't. Because as water forms on the evaporator coil, the process of that condensation will release the latent heat of vaporization, or latent heat of condensation. So that will increase the air temperature because we're releasing heat from that liquid into the air. So with a condensing dehumidifier, you'll always get an increase in temperature. So how does that look psychometrically? So with a condensing dehumidifier, our first process, if we're starting at a really high condition here with 33 degrees C, 18 grams, tropical environment, 58%. If we put that air over the evaporator coil, we cool the air down. Here we can see a 10 degrees C decrease in temperature. We're also seeing a 42% increase in relative humidity. But the coil's colder than this, so we then are at saturation, but we see latent cooling and sensible cooling even further. So this is where we see the dehumidification happening and the moisture condensing out on the coil. We then heat the air back up as it travels over the condenser. But we always get, again, that increase in heat from the latent heat of vaporization as water condenses and releases that heat on the evaporator coil. Now this also tells us that we have an issue when we go to a lower temperature. If we have a lower temperature requirement or a lower relative humidity requirement, then we're going to run into problems with a condensing dehumidifier. Because we're dealing with a direct expansion refrigeration system, we're limited by the apparatus dew point. Now, if the apparatus dew point, so the mean temperature across the coil, is, let's say, 6 degrees C, then we know that is the minimum absolute moisture content that we're going to get to. Well, if you take that up and heat that air up to 21 degrees C, we're going to be around 40–45%. So we know that if we go any further down, what's going to happen is that condensation will freeze on the evaporator coil. So you end up running defrost cycles, and you do more time defrosting the unit than you do dehumidifying it, so it becomes ineffective. So condensing dehumidifiers are typically used where they're effective, where the ambient temperature is over 20 degrees C and the desired set point is 50% or above. So lots of applications where that's really useful. But if your client says, no, I want 20 degrees C at 30% RH, it's never going to get there because your apparatus dew point will be below freezing. So we can't use that sort of technology. But there are different ways that you can install one of these systems. You can do them as a standalone system where you've got air just traveling over the two coils and then distributing into the space. You can have a ducted air supply so you can distribute the dehumidified air evenly. Very common to have a standalone system on a smaller application or something like a swimming pool. And these units, you can have them rear wall mounted, so you can have the unit in a technical area away from the clean room, or indeed you can have them ceiling mounted and then distribute the air across the room. Again, with the latter two, you would then have to have a remote sensor and control, so you're sensing air actually in the space. But again, if you can't satisfy your demand with a condensing dehumidifier, then we look at a desiccant dehumidifier that will work in much broader terms. It will work in a wider percentage of environments, lower temperatures, lower relative humidities. But it works in a completely different principle. Inside this box here, you've got a process air inlet fan, you've got a desiccant rotor, you've got a regeneration air inlet, and you've got a heater, a regeneration heater. So process air is taken from the space, typically, is passed over the silicon rotor, and water is captured in its gaseous form by the rotor. That then releases heat from that captured vapor into the airflow. So we get dry, warm air coming out of the unit. That gives us a problem because we've got a desiccant rotor that's captured lots of water vapor. So in order to get rid of that, we have to take another air supply from outside, run it through the fan, through the heater, and we dry out a section of that rotor by heating it up to 120 degrees C. That then dries the rotor out, and we have to then duct that wet air back to outside. So what does this look like psychometrically? Well, with the desiccant dryer, we start at, let's say, 23 degrees C, 9 grams per kilogram, 50% relative humidity. We then put the air through the desiccant dryer. We'll be going down the line of enthalpy. So we're increasing dry bulb temperature, decreasing relative humidity, and decreasing our absolute moisture content. And typically you will get 5 grams out of a system. But you will also get a residual amount of heat as the rotor travels from the regeneration air back into the supply air. So we need to consider that. Now, this also represents another challenge, because if we look at it psychometrically and the customer wants 20 degrees C and 30% RH, we're going to be just here. And we know the process is going to be following the line of enthalpy. So we have to work backwards. So if we follow the line of enthalpy back up, we know in order to achieve that 30% RH at 20 degrees C, I'm going to have to pre-cool the air that's required to go onto that desiccant rotor. So if I've got an ambient condition at 30 degrees C at 12 grams, I'm going to be up here somewhere. So I'm going to have to cool down prior to the dehumidifier and then dehumidify to get me down to the condition I want. So I'm going to pre-cool, but then I'm also going to have to think about post-cooling to cope with this regeneration residual heat. So with a desiccant dryer, I need to think not just about the dehumidification process, but I need to think about pre-cooling and post-cooling to ensure that we get the condition that we require into the room. So there are several ways that you can mount a desiccant dehumidifier. You can have them inside the room, so the blue box here represents the room. And if we've got air going from the room into the dehumidifier, over a filter, over a fan, water vapour is captured by the rotor, and then we get warm, dry air going into the space. Our regeneration air is coming from outside, going over the filter, over the heater battery, heating the rotor up and releasing that water, and then we're taking that wet regeneration air back to outside. Alternatively, we could have the dehumidifier outside of the space. Now here we're taking our process air from the space, taking deep to the dehumidifier, dehumidifying it, and then back into the space. And regeneration air is coming from outside through the heater, regenerating the wheel, and then taking that wet air back to outside. Alternatively, you could have an air handling unit and put the dehumidifier in line. So we could have an air supply going through a pre-cooler and preheater if required, through the dehumidifier, dehumidifying, releasing that heat energy as well, and then going through a post-cooler, maybe a post-heater when the controls call for it. And then a regeneration air is coming from outside, through the heater, regenerating the wheel, and then taking that wet air back to outside. Alternatively, we may have a high fresh air volume, but a low moisture removal rate. And when we do that, we can split the air. So if we've got our exhaust air coming to the unit or fresh air going in, we can take that air and we can take off, in this case, we can bypass 75% of the air and only run 25% of the air through the dehumidifier. We then over dehumidify that and then mix it back with the bypass air. In that case, we would then have the luxury of reducing the size of the dehumidifier because we're not having to dehumidify all of the air. We're just over dehumidifying a small proportion of the air, then mixing it back and supplying it into the room. And again, our regeneration air is coming from outside, going through a heater, regenerating the wheel, and then taking that wet air back to outside. So with a desiccant dehumidifier, any dehumidifier, to look at the loadings, very similar to the way we do with a humidifier, we need to look at outdoor air conditions, we need to look at the room set point, the moisture difference required, the air volume or the room volume, and the specific volume. And our duty calculation is exactly the same as it was before. We're just working down instead of up on the moisture scale. So our duty is going to be our moisture difference multiplied by the air volume, multiplied by 3600, divided by the specific volume. So very straightforward. But that's not the end of the story. With dehumidification, we need to consider what else is a moisture source within the room. Well, that could be the number of occupants and also what their working intensity is. And then if there's any additional moisture loads, like an open water surface or product moisture that's going to be released through the production process. Those two things will give us our total duty for the dehumidifier. So let's now look at energy considerations. And we talked about some good rules of thumb. We know every 1 kilogram of steam that we're producing for isothermal humidification requires 0.75 of a kilowatt. 1 kilogram of condensing dehumidification requires 0.5 to 1.5 kilowatts, again, depending on what your air on and air off conditions are. And 1 kilogram of desiccant dehumidification, somewhere between 1 and 3, again, depending on where you are between the start and the end point of the process. But it's a good indication. And for humidification, when we look at energy considerations, 100 kilograms of steam produced electrically will require 75 kilowatts of electrical energy. 100 kilograms of adiabatic plus gas preheat, that's still going to take 75 kilowatts, but the cost of the gas is lower than electric. But if we're doing it with free heat, then all we're running is some small pumps and valves. So that 100 kilograms would be down to 1.5 kilowatts. So it's really important to understand the system we're using and what the effects are. And of course, understanding that electricity is from sustainable sources. And with dehumidification, we've also got the option of being a little bit clever as far as our energy consumption is required, because the big energy consumption from a desiccant dehumidifier is the heater that's used to regenerate the wheel. So if we take our regeneration air and we heat it up and put it through the wheel, and then we take that wet air that's warm and we run it through a cross-flow heat exchanger, then we can preheat that regeneration air and reduce the load on the heater. And by doing that, typically we can get a 50% reduction in energy consumption. So there's lots of things to consider. And hey, we've come to the end of the presentation, pretty much on time as well, I'm glad to say. I'd like to thank you all for bearing with me through the presentation. We do a number of CPDs and presentations on humidification psychometrics, dehumidification drying, evaporative cooling, reducing ice and mist, control of static electricity, and this one in clean rooms. So with that, I'd like to then ask if we have any questions from our audience.
Yes, we certainly do, Dave. Yeah, thanks very much for that, Dave. That was excellent. Thank you.
Thank you.
Yeah, we've had a number of interesting questions, and some of them I'm going to merge together because they're roughly on the same sort of topic.
Okay.
The first one being, when I'm looking to dehumidify, is there a general rule in terms of picking the option of either a desiccant or a condensing dehumidifier?
Yeah, I mean, we covered a little bit in the presentation, and it's really down to the condition that you're trying to achieve. Anything above 21 degrees C and 50%, then a condensing dehumidifier is absolutely fine. But if you want a lower condition than that, then again, we're limited by the apparatus dew point of the system. If we try and operate a condensing dehumidifier at too low a temperature, then we'll get too much ice forming and spend all of our time defrosting the coils. So if you want a lower condition than 20 degrees C, 50% RH, I would always consider a desiccant dehumidifier.
Excellent. Thanks, Dave. You mentioned a HEPA filter. So with a HEPA filter, you said we need 2.5 times the steam absorption distance. What if we don't have this space? Is there anything else that we can utilize?
Yes, there is an option for that. You can use a we call it an Optisorb, a Condair Optisorb, which is basically instead of having one steam pipe with a number of holes in it releasing steam into the airflow, we have a manifold of steam pipes spread across the cross section of the air handling unit. And there we've got many more steam pipes with many more holes in it. And what that does, it spreads the steam across the whole cross section of the air handling unit or the duct. So you're introducing more steam to more air. And by doing that, because you've got a greater degree of exchange, that reduces the absorption distance. Sometimes that can come down to as little as 300 mil. But again, we must consider what the velocity is, what the air volume is, what the air on conditions are, and what the air off conditions are, because they will all have an effect on that absorption distance.
Yeah. Okay, another question. You mentioned when you're talking about the controllability and the controls of the humidifiers, you mentioned about the tolerance of the sensor. Is there a bearing on the sensor tolerance with relation to the RH tolerance?
Yeah, there is. I mean, every sensor will have a tolerance, and that tolerance will change as well when we get to the extremities of that sensor's operating window. So we know a typical sensor will have a variance of plus or minus 1 to 2% RH or 1 degree C. And if we've got a variance in the humidifier tolerance, let's say a humidifier is capable of controlling to plus or minus 5% RH, then that plus or minus 5% could be in absolute terms plus or minus 7 to 8. So yeah, sensor accuracy is definitely an issue. And you know, with sensors, typically you pay for what you get. The higher quality sensor, the more accurate it's going to be.
Yeah. Okay. We've got another question here. We have previously installed electrode type steam humidifiers. Would this be suitable for a clean room application, in your opinion?
That's a really good question. And the answer is yes, depending on what you're trying to achieve in the clean room. Now, an electrode boiler humidifier controls its output by passing current through water in a boiling vessel. And we modulate the output by changing the water level. So typically an electrode boiler will give you plus or minus 5 to 10% RH control, depending on the condition of the boiling cylinder. So if you're only looking to maintain a condition between 40 and 60% RH, so quite a wide tolerance, an electrode boiler should be fine, unless you're in a hard or soft water area.
Yeah.
If you're in a hard water area, then the unit will be doing more dilution cycle drains, and as the condition of the cylinder deteriorates over time, which they do, they're designed to do that, then you will struggle to maintain control because the unit will be doing too many dilution cycle drains. And typically in a soft water area, if you're operating up in Scotland, then there's not enough minerals in the water to pass current through the water to make it boil. So again, that gives you another controllability issue. So it depends what your water quality is and what controllability you're looking for. So electrode boilers in the right application, yes. Generally, we would steer towards a resistive heater unit so we don't get into those sorts of trouble.
That's great, Dave. Thanks very much. We've just literally had a flurry of questions in, so maybe if everybody doesn't mind, we're just running out of time now, so maybe we'll forward those answers on to you, if that's okay with everybody else.
Fabulous. Well, again, I want to thank everybody for joining the webinar. It's an absolute pleasure to present to all of you. And if you do have any applications for humidification, dehumidification, evaporative cooling, or evaporative cooling media, then please drop us a line or give us a call or check out our website. So with that, thank you again so much. You will get a link in about an hour's time where you'll be able to download your CPD certificate. So once again, thank you to everybody, and I look forward to seeing you all at the next one.
Thanks, everybody.